the talk of Professor Sukumar. The title is Mereology of Chemical Space and Chemical Libraries. Can you share? Yes.
Yeah.
Okay, I will raise my hand, my electronic hand, when you have 5 minutes left. Okay?
Okay.
Thank
Okay.
you.
Can you hear me okay?
Yes, we can.
Okay, great. Okay, so first of all, I'd like to say that I'm not a philosopher. I don't do research in philosophy. My research is in computational chemistry. My philosophical ideas might be half-baked, but you know, where my research interfaces with philosophical concepts, that's where I'm going here. So let's first talk about chemical space. As we know, space is big. Okay, as evidence for that, you can take the Douglas atoms if you don't want to believe astronomers. The Milky Way galaxy contains about 100 to 400 billion stars, and there are an estimated 2 trillion galaxies in the universe by decent estimates. So, in comparison, chemical space is vastly more huge. The chemical space of just the pharmacologically active molecules in cheminformatics is expected to be in the order of 10 to the power 60 molecules. Okay, and not only is it bigger in terms of the number of molecules, but even in terms of the dimensions, because chemical space is normally visualized in a multi-dimensional space of molecular descriptors. So you can have as many dimensions to the space as you can imagine molecular descriptors. So you're not just restricted to 3-dimensional space. So for instance, you have here a section of chemical space where you have the molecular mass versus the logarithm of the octanol water partition coefficient. So chemical space is traditionally visualized in a space of molecular descriptors, and this is used by medicinal chemists to visualize where their molecules lie in the space. And you can see here that the chemical space occupied by antibacterials is very much different from the chemical space occupied by central nervous system drugs. And this is important when you are searching for a drug for a particular condition. You want to be searching in the correct space. Okay. So, statement of the problem, this is a chemical library which is, let's say, a finite collection of molecules for a finite collection of discrete molecules assembled by chemists for some specific purpose. And you might naively say that, might expect that a library like this, being just a list, will have a simple classical Mereology. You can split up this list into 2 different lists, and put the lists together again. You have the original list, and the properties of the entire list should be basically the sum of these 2. Well, that's not really so, because of this, what I said here, it's a finite collection of discrete molecules assembled by chemists for some specific purpose. So the purpose, the function, comes in here. So the molecules in any library have some relation to each other, and because of that, the chemical libraries have distinct properties that are not identical to those of their sub-libraries. Okay. So so chemical libraries have distinct properties which are not identical to those of their sub-libraries or to that of their composite. So for many purposes, it is thus more useful to represent a chemical library as a graph or a network. So chemical space networks represent an alternate coordinate-free representation of chemical space. So here the axes don't have any specific meaning. And in this view, chemical libraries are graphs whose nodes are distinct molecules and whose edges are some pairwise relationship between the molecules. Now, where I am going with this is that the application of graph theory in science really probably started with chemistry, with chemical graphs of molecular structures and things like that. And we all know that a molecule is very distinct from just a jumble of its atoms. Okay, a molecule has distinct properties which are different from those of the collection of atoms. So if we visualize a molecule as a graph, and here we're visualizing a chemical library as a graph, so I'm arguing that the chemical library also has a different structure from its constituents. So a mathematical statement of this is that a chemical library is represented as a graph with nodes U, which are distinct molecules and whose edges E are some pairwise interactions between the molecules. So we can distinguish three different kinds of molecular networks. One is interaction networks, where the edges represent some physical contacts between different molecules or intermolecular interactions. For example, protein-protein interaction networks. Then there are chemical transformation or reaction networks, where the nodes represent metabolites or reactants and products, and the edges represent some reactions connecting them. And the third type is similarity or dissimilarity relations, where the edges don't represent a reaction or a physical interaction, but they represent a similarity relationship. They represent a chemical or mathematical similarity relationship between the molecules. So here we're getting more abstract. Okay? So to just give some examples here, this is the yeast protein-protein interaction network studied by Yildirim et al. Here the edges represent physical contacts between molecules or the protein-protein interactions. Okay. In a chemical transformation network or a reaction network, the nodes represent metabolites and the edges are reactions connecting them, example being the Krebs cycle, where each of these arrows is an edge and each of these boxes is a node. In similarity and dissimilarity relations, the edges represent a mathematical or chemical similarity relationship. So here is a network model of a diversity-oriented library. Here the similarity measure is defined using a set of descriptors or fingerprints, and then a threshold is set. And if we choose all molecules which have similarity greater than the threshold, that gives us a similarity network. And if we set a different threshold and choose all molecules which have similarity less than that threshold, we get a dissimilarity network. So here, this is actually a combination network where the blue edges represent the similarity edges and the red edges represent dissimilarity edges. Another example is the network of binding sites in the protein data bank. So we took the 108,000 odd binding sites from the protein data bank and computed shape property signatures using the BEST algorithm, which accounts for the distribution of polar and apolar regions and electrostatic potentials on the surface of the protein binding site. So this is a binding site similarity measure. It's not a whole protein similarity measure, it's a binding site similarity measure. So if two proteins, like say this protein and this protein, have an edge connecting them, that means that their binding sites are similar. Okay? So we expect that a ligand which binds to, let's say, this protein will also bind to or has a high probability of binding to these proteins because they have similar binding sites. So this it makes it useful for drug repositioning, so that if you find a drug for one condition which acts on one particular protein, then you can try that drug for the other proteins which are similar to it. Okay. This is another such network of the SARS-CoV-2 main protease. It's the protein ligand binding site network computed by my postdoc Sagar Bhaiye. So the this graphical representation of chemical libraries makes it easy to understand their non-classical mereology in the same way that a molecule consisting of atoms connected to each other by bonds is clearly more than just the sum of the individual atoms. And this non-trivial mereology of chemical libraries gives rise to a distinct eigenvalue spectrum that can be used to quantify the degree of randomness or otherwise of a chemical library. So just briefly to recapitulate some ideas about network theory, the most fundamental measure of a network is the degree, which tells us how many links a node has to other nodes. The degree distribution is the distribution of that of degrees. The probability that a selected node has exactly k links is the degree distribution. We see that for a random network, this is a Poisson distribution, and for the scale-free network, it has a power law distribution. Here, this is a log-log plot. So on the log-log plot, the power law is a straight line. Okay. And another measure is the clustering coefficient, which is the number of triangles that pass through any given node. So C of k is the average clustering coefficient of all nodes with k links. And we can see that this distinguishes scale-free networks from hierarchical networks, which again on a log-log plot has a straight line, because the clustering coefficient for a hierarchical network, it goes as k to the power -1. Okay. So we studied the behavior of large chemical spaces, and we found some 10 years ago, by studying this a large chemical library, which is the zinc database of commercially available compounds, which at that time had over 13 million molecules. Now it's about 20 million plus. That we see a linear relationship on a log-log plot of the degree distribution versus the degree, the probability of the degree versus the degree. The molecules here are represented as nodes, and the connections between them are defined by an atom type similarity measure. So it's a similarity between the atom types in each molecule. And the degree distribution follows a power law, which is k to the power minus lambda. Lambda is the power law exponent, and that gives a straight line because log p versus log k has a slope of minus lambda. Okay. Now, a useful measure to compare different libraries which may have different molecules and which may be described by different sets of descriptors is the edge density. And we can show that it has been seen that the edge density versus the threshold varies smoothly in this kind of arctan distribution. So the edge density is the fraction of pairs of nodes that are connected by an edge. So the maximum number of possible nodes is NC2, which is n into n minus 1 divided by 2, and is the total number of nodes or total number of molecules in the library. So the edge density is just going to be equal to the actual number of edges divided by this maximum number, right, or NC2. And it's can see that it's a function of the similarity threshold. So we compare networks with the characteristics, the network measures versus this edge density on the x-axis. So this is the degree centralization, which is the average deviation of node degrees from the maximum degree. And we can normalize to its maximum value for a star graph. And we can see that this is a chemical library, which is the library of glutaminase inhibitor molecules. And we can see that this has a much higher degree centralization. It consists of much more proportion of starry or hub-like nodes compared to this this line, which is the bottom line, which is the Erdo-Shreni random networks. We can also see that some nodes have outsized importance due to their betweenness centrality. So betweenness centrality is the number of paths that go from one cluster to another. So clusters of molecules belonging to different say, structure activity relationships are often not isolated into disconnected fragments, but are connected by chemical bridges, like molecules such as these, which account for a large proportion of the paths going from one cluster to another cluster. This is like, people who are, who you need to get to go through in order to connect to somebody else. Okay. These bridging molecules possess high betweenness centrality, describing the frequency of occurrence of a vertex on the shortest path between the pairs of vertices to the network. Its mathematical form is given here, and we don't need to get bogged down with that. Finally, we'll talk about spectral graph theory and random matrix theory. So the spectral graph theory is the study of eigenvalue spectra of matrices associated with a graph. There are two kinds of matrices which are widely studied. One is the adjacency matrix. For a finite simple graph, this is a square matrix with zeros along the diagonal and off-diagonal elements being 1 or 0, depending on whether the pair of vertices is adjacent or not. So aij equal to 0 if I equal to j and diagonal, and equal to 1 if the I and j are adjacent, equal to 0 otherwise. If the graph is undirected, the adjacency matrix is symmetric. Then the Laplacian matrix is the diagonal matrix of the degrees d minus a. Okay, so it's equal to the degree if I equal to j for the diagonals, and equal to -1 if the nodes are adjacent, equal to 0 otherwise. So for example, for a graph like this, the adjacency matrix can be calculated like here. So node 1 will be connected only to node 2. Node 2 is connected to node 1, node 3, and node 5, and node 6, and so forth. And since an undirected graph is symmetric with 0 and 1 entries, the eigenvalues of its adjacency matrix are real. The Laplacian matrix can similarly be calculated. So D is the degree. So this is node 1, this is node 3, and so forth. And if you subtract D minus A, you get this. And we can talk about the algebraic connectivity or Friedler eigenvalue of a graph, which is the second smallest eigenvalue of its Laplacian matrix. And its magnitude is a measure of the overall connectivity of a graph. So we can see that if a graph consists of disconnected pieces, then its secular determinant factors out. Its adjacency matrix factors out, and therefore the secular determinant, which is the determinant of A minus lambda I equals 0, this also factors out. So this will consist of a block, a 4x4 block of a determinant, which has 4 eigenvalues, and a 3x3 block. Okay? So in this case, this piece and this piece have a classical Mereology. But this is not true for the nodes inside this piece or the nodes inside this piece. Okay? So to see that, if we take a node which is not connected to any other node in the network, it contributes 0 eigenvalue because all its off-diagonal elements with other nodes are 0. If we have an isolated edge, that is 2 nodes connected by an edge and not connected to any other node in the network, then that contributes a ±1 pair of eigenvalues. You can see that this will be the adjacency matrix of this piece. And so the block of the secular determinant will be minus lambda 1, 1, minus lambda. And so its solutions are lambda equal ±1. We can take that for triangles, and we can see that each isolated triangle will contribute an eigenvalue 2 and a pair of degenerate -1 eigenvalues. For a fully connected graph, this will reduce to 2 -1 -1. If for an isosceles distortions, that is, if you break this edge, then you get 0 and ±√2. And if you break these edges, then you get 0 and ±1. So the take-home message is that these -1 eigenvalues and these 0 eigenvalues can arise due to multiple reasons. So it can arise from isolated triangles, isolated edges, and things like that. So there are many different ways in which these can arise. And we can look at varying the connection, and you can see how these transform into each other. So finally, coming to random matrix theory, which was introduced by Wigner in nuclear physics. And it's been used, it captures the universal and generic properties of the system. It has been used in various fields for complex networks, protein-protein interactions, metabolic networks, and so forth. And for a random network, it has this Wigner surmise, which is a semicircle distribution of the eigenvalues converged to a semicircle. Here we study the eigenvalues of the adjacency matrix for chemical similarity networks. And there are, so the spectral density is given by a formula like this. And we can see that for chemical networks, we have plots like this, whereas for the random network, you have a semicircle density. Okay, so the
we have almost not time for questions if you don't finish. Thank you.
2 minutes more, right? So here so we can see that, so then there we can define short range correlations through the nearest neighbor and next nearest neighbor spacing distributions, and long range correlations through a measure called the spectral rigidity. We don't need to go into these formulas. We see that for different networks, they all follow this prediction of random matrix theory, which is a Gaussian orthogonal network. So this is for the glutaminase C library. This is for natural products libraries from the zinc database. So this is for the nearest neighbor spacing distribution. Same thing we can see for the next nearest neighbor spacing distributions, again for the glutaminase C library and the natural product libraries. For the ratio of consecutive spacings, again we see they all follow this Gaussian orthogonal ensemble. However, for the long range correlations given by the spectral rigidity, the glutaminase C network, which is a focused library, follows the Gaussian orthogonal ensemble, whereas the natural product libraries, which are more diverse libraries, they deviate from Gaussian orthogonal ensemble at high edge densities. So I'll skip the discussion of activity cliffs, and we'll just go to the conclusions, which is that a chemical library can be represented as a graph or network with non-trivial mereology, and spectral graph theory and centrality measures provide useful tools to probe the mereology of large chemical networks. And these statistics quantify short-range spectral fluctuations. They exhibit universal behavior and follow Gaussian orthogonal ensemble for various chemical spaces. But spectral rigidity, which encodes the long-range fluctuation statistics in eigenvalue space, the correlations between eigenvalues which are distant from each other in eigenvalue space, they respond to measures which not only network structure but also the chemical space. So you can use that to distinguish between different kinds of chemical spaces. And understanding these connections with spectral rigidity can help us understand the mereology of large chemical spaces. So I'd finally like to thank the people who did the work. This is my colleague, Professor Santosh Kumar from physics, Professor Sudipto, who is an expert in random matrix theory, Professor Sudipto Bhattacharya from maths, who is an expert on networks, my postdoc Sagar Bhaiye, Michael Klein, who did the analysis of the protein data bank and the large chemical spaces, my PhD student, former PhD student Ganesh Prabhu, and my current PhD student Manuja Kotyal, who is studying the random matrix theory and its applications to chemical networks. And thank you all for your attention.
Well, we have time only for 2 questions. We have 2 questions already because we have only 5 minutes. The first question is written here. He says, what is the conceptual definition of classical mereology apart from the mathematical definition you gave in terms of matrix factorizability?
Okay. The way, okay, this may not be a formal definition, but the way I would say it, that is that that the sum of the parts gives you the total. Okay, so if you have a bushel of wheat, you can divide it into 2 bushels, and they basically you can put them back together. Or yeah, so that's the thing, as opposed to components which have interactions among them or correlations among them, which cannot be unentangled in this way.
Okay, thank you. And we have a final question from Guillermo Restrepo.
Okay, yeah, thank you for the talk. I see that this is very interesting, that connection between chemical library, chemical space, and networks. I have several comments, but perhaps the most important one is that there are several works by Ron Harre and Jean-Pierre about the Mereology or different Mereological aspects of chemistry. And then the question is, what is the advantage of bringing this setting that you have shown of chemical networks from the perspective of Mereology? What's the advantage for philosophy of chemistry and for chemistry of using this setting?
Yeah, I think the different concepts of Mereology have a relationship to the mathematical concepts of homomorphism and diffeomorphism and things like that. I'm not very very familiar with these, but I think that is where the studies have been done on graphs, on the subgraphs of a graph and so forth. But what I'm looking at here is the eigenvalues and how those eigenvalues relate, eigenvalues of the subgraphs relate to the eigenvalues of the entire graph, and that is a totally non-trivial relationship unless the subgraphs are completely disconnected. Okay, so even if you have a few connections between 2 subgraphs, that completely changes the eigenvalue spectrum. Okay.
Yeah, that I understand, but I see that you are replying from the side of mathematics. You are telling me some advantages, or that those statistics are telling me something about the network. But I would like to know what's the insight we can get from that in chemistry and in philosophy of chemistry.
Yeah, so for instance, the reason why we were studying this is whether we can use this kind of statistics to distinguish different libraries, so or different kinds of libraries. So we're looking at focused libraries where you have a group of similar molecules for a particular target. So let's say anti-cancer molecules or something like that, and a diverse library which consists of all kinds of diverse chemicals. And we find that we can distinguish between these 2 classes of molecules from this eigenvalue statistics, but from the long range spectral, the spectral rigidity function. Okay, so some measures are able to distinguish them.
I invite you to continue in the room, in the coffee break, because we are in time. Thank you very much.
Thank you.